Entropy and enthalpy. Entropy is represented by delta S. So what is entropy? Well, it's a measure of energy dispersal in a system or the ordering/disordering of a system. For the equation, it is delta S of the products minus delta S of the reactants, but most of the time you'll not have to calculate for entropy, but you rather just need to know whether it's negative or positive. When delta S is greater than 0, the products are more disordered, but when delta S is less than 0, the products are more ordered. To determine if delta S is negative or positive, you can look at the equation. If the reactants are going from a solid to a liquid or a liquid to a gas, delta S will be positive, but if the reactants are going from a liquid to a solid or a gas to a liquid, delta S will be negative. Another way to determine the sign is by looking at the number of moles on both sides of the equation. For example, in the decomposition of calcium carbonate, there is 1 mole of reactants while there is 2 moles of products, so delta S will be positive because it is getting more disordered. In the first example, nitrous oxide gas separates into nitrogen gas and oxygen gas, which would have a delta S sign that is positive since there is more moles of products than reactants. For the second example, H2O gas is changing into a liquid, so delta S would be negative because the product is becoming more ordered. Enthalpy. Enthalpy is represented by delta H. So what is enthalpy? It is the energy associated with the breaking and forming of bonds in a chemical reaction. There is 2 equations for enthalpy. One is bond energy, which is bonds broken minus bonds formed. The second is the heat of formation, which is the delta H of the products minus the delta H of the reactants. When delta H is greater than 0, the reaction is endothermic, so heat is a reactant and the system has gained energy. But when delta H is less than 0, the reaction is exothermic, so heat is a product and the system has lost energy to its surroundings. In example 1, it shows the use of the equation of the heat of formation. It takes the delta H values of the products and subtracts it from the delta H values of the reactants. For example 2, it demonstrates the use of the equation for the bond energy by adding up the bond energy values of the reactants and subtracting it from the bond energy values of the products. Next is Gibbs free energy. This equation helps to determine if a reaction is thermodynamically favorable. It is delta G equals delta H minus T times delta S. Delta G equals Gibbs free energy, delta H equals enthalpy, delta S equals entropy, and T equals temperature. If delta H is positive and delta S is positive, it's only favorable at high temperatures. But if delta S is positive and delta H is negative, it is always thermodynamically favorable. If delta S is negative and delta H is positive, the reaction is never thermodynamically favorable. But if delta S is negative and delta H is negative, it's thermodynamically favorable at low temperatures. In this last example, the given is the equation, which is the forming of nitrous oxide gas, and delta H is also given. Delta S would be negative because the solution becomes more ordered, but delta H is positive because it's an endothermic reaction. Then, since delta H has the degree symbol, it means that it is at standard temperature, which is 25 degrees Celsius and 298 degrees Kelvin, which would make temperature positive. So delta G would be positive, which is never thermodynamically favorable.